Hey everybody, it's Mrs. Cat here to talk some more about volume. Since the first time that we looked at volume in the first part of the volume 3 levels diagram, you hopefully have done a few more things with volume. You should have watched a video from Mr. Sharkey about how to collect volume measurements in both cubic centimeters and milliliters. Watched a video from Mrs. Bellotti about how to graph data using a scatter plot in Google Sheets and how to add a trend line with an equation to that graph. And then you should have done the comparing volume lab and ended up with what you see here on my screen. Today I'm going to talk just a little bit about what we need to get from this comparing volume lab, and then we're going to add some of those things into our 3 levels diagram. So what we've got here is a scatter plot showing volume in milliliters versus volume in centimeter cubed. And we added that trend line, and the equation for our trend line is going to be what we want to focus on for right now. And that equation should be what we see here, which is going to be y equals 0.958x plus 1.21. Now, you may have wound up with some more digits for each of those numbers there, but the important part is what we get from that equation. Now, I'm going to focus on this equation for now, so I'm going to scroll my graph out of the screen. What we have this equation here is this is our linear equation, which is in slope-intercept form. So just as a little refresher, slope-intercept form is y equals mx plus b, where slope is represented with m and our intercept is represented with that letter b. Okay. So we really want to focus in on slope, but since we're talking about this here, let's go ahead and talk about what both of those things are. Okay. Slope tells you what's happening with your line. In your reflection question, I saw a lot of really good responses to what does the slope tell us, but quite a lot of those were pretty generic. So I got things like slope tells you that it is positive, or slope tells you y over x, which that's true, but we want to really get down to what this specific data is telling us. So slope is going to tell us the change in y variable over the change in our x variable. You probably have also seen this in math as y2 minus y1 over x2 minus x1. Now for us, our slope is that 0.958 value. So for us, what we're seeing for our slope is that our slope is 0.958 over 1. We don't have anything else there to tell us what's going on. Whenever you have a decimal number, we're going to make it a fraction by putting it over 1. Now, if we look back at our graph, we'll see what our values are being graphed as far as our y and our x variables. For us, we've got y as milliliters and x as centimeters cubed as far as our volume units. So I'm going to go ahead and add this in to my slope. And what you can see very clearly here is that we have a relationship between milliliter values and cubic centimeter values. Okay. This is a proportion. We kind of talked about proportions when we did our boat building activity and we analyzed the score for our boats. Okay, you could also write this as a ratio, but what we really want to focus on with this is that relationship between the two. So what we can say, if we want to write this out in a sentence, that we could say for every 0.958 milliliters, there is 1 cubic centimeter. Now, those values could be interchanged as far as the order in our what we call a for every statement. We could say for every 1 cubic centimeter, there is 0.958 milliliters. So that's just showing our relationship. What this really gives us is a conversion factor. We could use our equation, we could use this relationship to go between volume in milliliters and volume in centimeter cubed. Now, this is data that was collected by a human being. This is not perfect data. So the relationship between cubic centimeters and milliliters as far as volume is concerned is not 0.958. Instead, our true relationship is, let me change colors to make this stick out here. For every 1 milliliter, there is 1 cubic centimeter. Okay, so this is really our relationship. Okay, they are equal. Okay, they are equivalent units. So what I'd like to do is to go ahead back to our volume 3 levels diagram and add this in. This is going to go in our symbolic space. We really don't have much in there now, but let's take a look at what we can add here. So right now in our volume 3 levels diagram, we've got some information about how you can find or calculate volume of a solid or liquid. I'd also like to add in here a sketch of our graph. So let's label our axes, milliliters and centimeters cubed. Because we want to, let's try that again. Because we want to represent our true relationship, we want to show that slope is equal to 1. Okay. Now, what this tells us is that we have 1 milliliter for every 1 centimeter cubed. Okay. Let's go ahead and write these out, right, as our for every statement. For every 1 milliliter, there's 1 centimeter cubed. We could also write this as, let's see, I'm going to write this as volume in milliliters equals volume in centimeters cubed. Okay. And if we want an example of that, let me just kind of squiggle this here. 25.0 milliliters equals 25.0 centimeters cubed. Yeah, I don't like that there. Let me move. It's outside of the box, but that looks a little bit better. Okay, now we could show this graph with our axes switched. Okay, we could have centimeters cubed on the y, milliliters on the x. We would still wind up with a slope of 1. Our slope units would be flipped. We'd have centimeters cubed over milliliters, but it would still be the same relationship. Okay, that's not always true, but it is here since it's equivalent, 1 to 1. Okay. Some other things that I'd like to add to our 3 levels diagram would be in the macroscopic space. We know that volume is 3-dimensional, but I also want to add one thing that I saw a lot of students comment on in the reflection question, and that is how to measure volume. I saw a lot of students mention volume displacement. So let's add that here. So the volume displacement method for measuring volume of an object is where you're going to take a measured volume of water, add your irregularly shaped object to that water, and then measure the change in the volume. So I'm going to do my best to sketch a graduated cylinder. Okay, let's see here. Here's my after. They're not going to be identical, but let's pretend like they are. Okay, so I'm going to fill in a volume measurement. Before, I'm going to add in an irregularly shaped object. Let's say it's a, I don't know, piece of metal, right? So So we're going to add it in, and it's going to cause the volume inside the cylinder to increase. Yeah, let's re-add that piece of metal on top. Okay. Let me just make it darker. There we go. And then we can show that the volume of the object is equal to the change in volume, which again, that's always going to be final minus initial. But if you have something that's oddly shaped, this volume displacement method is going to be the way to go for your volume measurement. Okay, so we're going to do a little bit more with volume as we move on to our next lab activity, looking at the relationship between mass and volume. We'll revisit volume and throughout some different units throughout the year, so please make sure that you hold on to this 3 levels diagram because we will come back and add more to it. Thanks.